Good morning, good afternoon, good day, ladies and gentlemen. Welcome to the final part of our webinar series, Structural Welding Simulation with Simufact Welding. I will introduce myself in a couple of minutes, but for the first glance, we take a look at what we are doing today. So basically today we continue our webinar series started a couple of weeks ago, and we go a bit deeper into details of how structural welding simulation works and what to expect in the next future. As a preliminary information for you, this webinar is recorded, and the recording will be made available for participants a couple of days later. With a bit of luck, maybe already tomorrow. If you have any questions, I would kindly ask you to use the question and answer window on the right side of your screen. And after the webinar is over, I will try to address your questions at the best as I can do. My name is Pavel Khazan. I'm product owner of Simufact Welding, and basically responsible for software development and more or less for things that will happen next. Our agenda for today, I will give you a brief history of welding simulation at Simufact, an overview and a bit of background of structural welding simulation in general. We will discuss a bit the model components needed for fusion welding, basically the basic welding process we are usually looking at. Take a look into some special cases, into result evaluation, and we will take a brief look on possible future development path. So Simufact Welding was born around 15 years ago as an idea to create a user-friendly tool specialized for welding simulation. It should be close to production, so someone who can do welding in real life should understand how to make the simulation. It should be open, it should use a good solver technology, and it should especially be adapted for welding simulations. So the first stable released version was released in the year 2012. And from then on, we have developed a lot of additional things and modules, like resistance spot welding module, added some fast approaches. I will talk about them a bit later. Implemented solid shell elements into our solution, as well as some internal measures. Went for new material models and contact tables. And finally, with the last release at the beginning of this year, we went for direct energy deposition and also a scripting interface using the Python programming language. A brief overview and a bit of background of structural welding simulation. Since approximately 70s, so basically something about 50 years, three general areas of interest that describe phenomena of welding simulation have been identified. They are very different in terms of requirements on mathematical and physical models, and were described in detail by Professor Radai 2012. So basically, the welding simulation is subdivided into three areas. We have the process simulation area, where we take a close look into weld pool geometry, local temperature fields, efficiency. So you might know, if you use, for instance, laser for welding, that not all the energy you input in your process is really present in the process itself, because of some absorption effects and reflection effects. Process stability, for instance, something like humping if you weld too fast. Then we have material simulation, what happens with the material due to energy input, due to heating up and cooling down. And we have the structural simulation, basically looking at global temperature fields, distortions, residual stresses, structural behavior. So not that much into the detail of the melt pool, or, for instance, a spot weld during spot welding, but more or less globally on what happens to the structure. So the first one, the process simulation, of course, describes the process properties. And the last two items would describe structural properties, because, of course, material behavior is also important for properties of the structure, for deformations, stresses, and so on. So basically, Simufact Welding is at home in these two areas, structural simulation and global material simulation. The coupled thermomechanical structural simulation, as the name already says, it has something to do with temperatures, it has something to do with mechanics, and something to do with structure. Is usually used for a lot of fusion welding processes like laser welding, arc welding. Brazing is a specialty, and electron beam welding, and is once again subdivided into three areas. So we have at the beginning the temperature field. From the temperature field, we have some changes in the material, and we have, of course, also some changes in the structure itself. So all of this is connected somehow. And to achieve this, some certain model components are needed to be able to set up a model and to be able to calculate it and get some meaningful results. So for the beginning, we need, of course, a geometry describing how the model looks like, what are the components we are welding together. We need a definition of weld path, so how the heat source is moving. We need tools, so basically fixtures, clampings, and so on. They can be idealized in a sense that nodal boundary conditions are used. They can also be, like in our case, usually real two geometries with, for instance, forces or stiffnesses applied to them. We need some type of heat source definition. We will look into it a bit in detail a bit further. We need a material definition, so how the material behaves under thermal or mechanical loading. And then, of course, there is a solver which somehow gathers all this information and does some calculation. And afterwards, we get the results, and those results have to be evaluated at the end. We start from the beginning with geometries. So basically, in our software, for simple geometries like sheets, plates, cylinders, and so on, it is possible to define the geometry directly into the inside the software. So there is no need to use some external CAD tool. So if you are just about to weld two plates, then this works basically just out of the box. Of course, the general case is a more complicated geometry, and this geometry is present as some type of geometrical data, CAD data usually. So we are, of course, able to import, as you can see on the screenshot, a lot of formats, either already meshed geometries or geometries present as CAD data here on the right side. We also provide a so-called welding Apex bundle. So Apex is a tool from MSc software, which basically is a relatively powerful CAD tool, which is able to create and manage and edit CAD geometries, as well as create finite element meshes needed for the calculation at the end. So either with these filters or with welding Apex bundle, it is possible to create and use basically any kind of geometrical data you have available. For numerical calculation, we do not need the geometry itself, so the CAD data is nice but not sufficient. We need discretization of this geometry, so at the end, so-called volume mesh. And once again, simple geometries like plates, sheets, cylinders, and so on can be meshed with internal measures directly in welding itself. So basically, if I start with this type of geometry here on the left, I go through the measure and I get a relatively nice, actually, mesh on this geometry, also with refinement boxes at the positions where I would like to weld, because, well, where welding happens, the temperature gets high, and where the temperature is high, I would like to have a finer mesh than here in the center of the geometry, where maybe nothing happens. The meshes have to be positioned, so it is, of course, possible to position them directly in your CAD software, but it is also relatively easy to position them directly inside welding. Of course, we support the usual positioning methods like translation and rotations, but also so we support so-called contact positioner. So basically, it is possible to say those two parts are going to be in contact. Please move them accordingly. This can also happen based on gravity. So then this is a real small kinematic simulation which is happening there, or based on relative positions of edges and corners of two selected geometries. After we have the geometry of the part itself, we also need geometries of tools and clamps and fixtures and so on. So simple ones like plates, cylinders, cubes, and so on can be once again created and positioned directly in welding. If you have a big fixture with a lot of single clamps, you probably will have some kind of CAD data for it. This CAD data can be imported and directly used in the simulation. At the end, it's all about the shape of the contact area between tools and components. So basically, you can see here on the picture two different clamps. The left one looks more sophisticated. The right one is very simple. At the end, it doesn't make much difference in the simulation itself, because the contact areas of these both clamps are more or less the same. The clamping tools themselves can be defined using a prescribed movement, so they can have some starting position, some end position, some velocity, prescribed forces and stiffnesses, and they can be time controlled regarding turning them on and off during the calculation, fixing them for a certain time period. All these definitions, like stiffnesses and so on, can be done using constant values or different tables. So if I have a full description of a tool, I have certain translational stiffnesses, I have rotational stiffnesses, and I can also control the rotation around the z-axis if it is needed in the simulation. So at the end, such type of a tool can not only be used as a fixing tool, but also can be used for simple forming simulation. And here we have an example of a deep drawing simulation performed in welding on a welded part. So basically we have a tool with a certain kinematic which takes a welding part and deforms it in the desired way. So the clamping tools are not only limited to fixing the geometry, they can also be used for deformation if needed, or something like, for instance, pre-bending. Of course, for the welding process itself, the heat situation, the temperature situation is very, very important. So one has to take care about things like thermal boundary conditions. Those are defined in our software using a radiation and convection coefficient. On contact surfaces, it is possible to define a certain heat transfer. So if a hot body comes into contact with a cold body, the thermal energy flows from hot to cold. And those coefficients also can be automatically determined due to surface stress, surface normal stress. The temperature of surrounding medium is of course taken into account because due to this temperature the cooling happens, and it is of course possible to define initial temperature. Besides that, we have certain initial conditions for mechanical simulations. So, for instance, it is possible to define for steels initial phase proportions. So if you use a steel grade which underwent some type of heat treatment with some metallurgical phases created during it, you can start your simulation with these known phase fractions. It is possible to define a plastic strain. So if you have done some pre-hardening, for instance, then this plastic strain would take care that the stiffness of the material grows. And it is possible also to use gravity in the simulation. So after we have our components, tools, and boundary conditions, we have at the end a geometry. So we have here this gray plates being components to be welded, and we have this red and blue plates being idealized, in this case, different tools. After we have this, we need a weld path. The weld path can, of course, be defined on the model itself, which is very easy to do for straight lines and very easy to do if you only have a couple of weld lines. But of course, if you have more than a couple, it is possible to import them from a table. And in the more general case, if NC code or some type of G code is present, it is also possible to use it directly to create weld lines inside a model. Besides weld lines, we of course need some type of additional material. There are processes without additional material. There are processes that require additional material. So the usual case for arc welding, one usually needs some additional material. For instance, laser welding, it might be the case, it might be not the case. It is of course possible for this so-called weld bit or fillet to use some imported mesh or mesh CAD file. Otherwise, it is also possible to create a lot of shapes directly and automatically in welding. So basically, we have a tool which follows the trajectory, the weld line, and creates a fillet of a given cross-section shape along this weld line. One important thing is, of course, the description of heat source, because the heat source is basically the welding process. And in the structural welding simulation, we usually use the so-called equivalent heat source. So a mathematical description, more or less, which describes heat flux in a given volume with respect to velocity, power, efficiency, and the geometrical description. So usually the heat source has to be calibrated or calculated prior to the simulation. There are certain tools around that are able to predict how this equivalent heat source should look like based on process parameters. The usual way is, for instance, for laser welding, is seen here that one measures the intensity and then changes the parameters. As you can see, there are a lot of parameters here present to make them somehow match with the measurement. Otherwise, it is also possible, of course, to take a look at the metallographic cross-section, see the heat-affected zone, see the molten zone, and just play around a bit with the heat source geometry and other heat source data to come close to the measured dimensions. For this, we offer a purely thermal simulation, which is sufficiently fast. So it is possible to make a couple of quick runs to see how the heat source reacts and how the melting zone and the heat-affected zone are created in the model. For material data, we usually need temperature-dependent data, so basically density, specific heat capacity, heat conductivity, and then mechanical data like Young's modulus, stress-strain relations, Poisson's ratio, and thermal expansion coefficient, as well as for metallurgy, so for phase calculation, some data about transformation kinetics. And of course, in this case, we would also need properties of distinct phases, because of course, if all phases have the same properties, then there is no need to calculate the phases. So around about 40 material data sets are included already in the setup. They can be edited manually. So if you, for instance, know that you have a certain steel grade, but the documentation says that the yield strength is 10 megapascal higher than you have in the database, it is possible just to scale the database. So within a certain range, it is possible to play around a bit with already existing data without much loss of accuracy. And if this is not helpful, we also have an interface to material simulation software GMAT Pro. GMAT Pro is a third-party tool which is able to calculate needed material properties based on alloy composition, as well as, if needed, heat treatment history. So basically, with the already provided data, we have a lot of general steels, aluminum, titanium, and some nickel-based alloys present. The database can be extended if needed. After all, if we have everything together, we have this brief time overview, also called Process Control Center, where we can see, for instance, that we have a process taking overall 300 seconds. Here at the beginning, we have a couple of welding robots welding a couple of weld lines. So in this case, each of them welds 4 weld lines. And then we have tools that are getting activated, deactivated, and so on. So after all, during cooling, we can basically deactivate all the tools and have some type of, well, 3-point bearing here, allowing for free deformation. Sometimes one also wants to use a tool until the end. It is also not a problem. The solution procedure itself, just a brief overview. So we start with calculation of heat fluxes and check if the heat fluxes are in agreement with the input. So the reason is basically if the mesh density changes below the heat source, it is possible that the calculated heat flux is a bit off. So the solver corrects this small error in every increment. And then from that, we calculate the transient temperature field, so basically solving the heat transfer equation with all the material data that is present. We do an error estimation. If the error is inside the limit, then we continue with recalculation of material data. Material data changes due to temperatures. With this new material data, we calculate strains. So we start, of course, with thermal strains, and out of them, they induce basically deformation stresses, maybe changing contact situation. A gap might close or a gap might open up. And during this process, we calculate the force balance, element quality, and if needed, the calculation is done over and over again. If we are done at this point, then we spring back to the next time step, to the calculation of heat fluxes for the next time step based on deformed configuration from the previous one. So this is basically what a coupled analysis is doing. And this coupled analysis has one disadvantage. It's very precise, and this is good, but the bad thing is it takes a lot of time because we need somehow to do it. We need to resolve the movement of the heat source. So the time steps are sufficiently small. We have a lot of small time steps means we have a lot of calculation time. So to speed up this a bit, we have proposed also a transient decouple simulation. So basically, this means not every thermal step is followed by a mechanical step, by the but we skip a bit, a couple of them. So the results are maybe not that precise, but the calculation time decreases largely because, well, mechanical calculation is more expensive in terms of calculation time than thermal simulation. Then we have the so-called thermal cycle method. So, for example, if you have a very long and very straight weld line, it takes a lot of time steps to calculate the movement of the heat source along the weld line, but the most important effect here might be the shrinkage effect. To capture it, it is maybe sufficient only to heat up the weld line at once. So you get the deformation, but it's once again less precise as you would get from the transient mode. The speed up is depending on the length of the weld line. So, for instance, for a usual weld line, the thermal cycle method would need maybe 10 to 20 time steps, while depending on the length of this weld line, the transient method would need maybe thousands of time steps. If one would like to neglect the welding sequence, it is also possible to use the so-called one-shot or single-shot solution. This would mean that the thermal cycles are applied at once on all weld lines. And one step further would be the shrinkage solution, meaning that the material behavior is linearized and we only take a look at the shrinkage appearing due to cooling of weld lines. At the last point, we have the fast thermal simulation. So this is basically used to calibrate the heat source to see the temperature fields, maybe identify some hotspots, overheating or underheating, which is basically very fast and has also, in terms of temperature fields, a very high precision. Can also be used to investigate the cooling behavior to see what happens with, for instance, metallurgical phase transformations. So basically those three approaches are the interesting ones if you try to compare several assemblies between each other, because they are sufficiently fast to allow you to calculate a high number of models in a relatively short time period. To see what happens here in reality is one example. So we have this assembly which was sufficiently large, something about 2.5 meters length, with a couple, I guess 10 or something like this weld lines. And we got a transient calculation time of 86 hours. Going to single shot reduce the calculation time to only 2 hours and a couple of minutes. And what you can see, of course, that the total distortion value here is different from the total distortion value here. So we have here 3.2 millimeters, here we have 2.3 millimeters. But if the question is where do I expect the deformation, then this simulation is basically sufficient because the deformation happens here and here, so basically on the same position where also can be seen in transient simulation. And also the order of magnitude of the deformation is not that far off, actually. With the frequency simulation, we once again see the correct positions, but the total distortion is by a factor of almost 10 below the transient simulation. So it's less precise, but it's once again faster. It took only 8 minutes. Shows the position of distortions, but not that much the real distortion value. Let us take a look at some special cases. So besides fusion welding, we also offer a solution for resistance spot welding as a global process model. The global process model, the process model means we do not use equivalent heat source here, but really in general really force and current and generate heat out of the current. Since a couple of months, we have a deposition welding module allowing more or less 3D printing with lasers or wire. We have two auxiliary modules, so heat treatment. So you can do a heat treatment on your welded part and see things like, for instance, stress relief. And also an auxiliary module, cooling and clamping, usually used if you have a very, very big assembly with some sub-assemblies. So you simulate your sub-assemblies separately and then put all of them together to make a big model out of a lot of small models with results from small models. In resistance spot welding, we basically do a real process simulation, including a comprehensive electrode database, and we define currents and forces over time. So basically the heat is generated due to current and due to resistivity of the material and contact areas. Of course, once again, if you have a very, very big model, this takes a lot of time. So there are certain simplifications. So it is possible to replace the current definition by the temperature curve definition. So once again, it's kind of thermal cycle where you define the geometry of the weld nugget and the temperature that the weld nugget experiences. It is possible to use, once again, the one-shot or single-shot solution where we can weld several or all spots at once. And it is possible to use a purely mechanical solution, so basically only the pressure of electrodes. I have done a small investigation about it. So this is a model, basically 3 components with something about 15 to 20 spots. If I replace in this model the transient solution by thermal cycle, I already save almost half of the calculation time. Of course, it depends a bit on the model itself. The mechanical solution cuts it down to 13%. And then if you go to single shot, you also land here somewhere between 13 and 15%. In the mechanical single shot at 2%. One has to understand that the single shot solution neglects the welding sequence, basically. And the interesting thing was that the deformation was in all cases in the same order of magnitude. The reason for it is that for resistance spot welding specifically, the global deformations, not that much the deformation inside the spot, but the deformation of the structure itself is very related to clamping conditions and electrode forces. Because this small heat input inside this very, very small spot has not much influence on the global deformation if the structure is sufficiently large. So basically, the mechanical single-shot solution was already very, very good. The one thing which was not that good was the calculation of stresses, because, of course, due to missing temperature field, the material behaves differently in the purely mechanical case. So this is the reason why stresses are. So this is the reason why you need the temperature fields if you would like to move into stresses. The new deposition welding module basically is based on the so-called direct energy deposition process. So a brief overview for the process idea. The process itself is based on heating of deposit material up to melting temperature and deposition of the material on a base plate or some other base geometry. It can be whatever you want. There's no need to have a plate for it. And there are basically 2 approaches, the powder approach and the wire approach. The powder approach brings powder into the process with some powder nozzles. There are several types of them. And the wire approach brings wire into the process, also with several different geometries. The powder approach is usually used with laser heat source. Wire can be used with laser and also with arc. So this is basically the process idea. And we have done some research work on it and came out with at the end with a deposition welding module. So what we see here is this typical blade geometry used for some testing and investigations. The measurement comes from our partners at Fraunhofer Institute EPK in Berlin. So they have basically welded such type of structure, and they have also measured the deformations. And we can see that the deformations are basically kept here on the right side, are basically caught really good by simulation. What is also possible is, of course, to simulate what happens if I separate this component from the base plate. So we have some bending upwards and we have some bending to the side because the stresses after cutting are released. And we see basically that the results are very good corresponding with measurements, even after this non-standard wire cutting procedure. So this is how the simulation afterwards looks like. Basically, what we see here is a displacement that is built up during the build-up process of the blade. One word or a couple of words about the result evaluation. Of course, after the calculation, we have transient fields, so we can just take a look into our model and see that, for instance, here the effective stress is somehow concentrated here in the corner, and here we have this blue area with relatively low stresses. It is also possible to evaluate these fields in some custom coordinate system. Imagine if you have a measurement table and you do some measurements on your welded assembly. The coordinate system of the measurement table is usually different from what you have during the process or in the model. So it is possible to transfer the model into a certain coordinate system to make a measurement. It is also possible to use best fit algorithms. So if you have, for example, a measurement, surface scan or something like this, you can bring this measurement into the software, and then the welding assembly is oriented to match this measurement, so you really see the deviation of the surfaces and not that much the absolute values. It is of course possible just to select certain points and to export the data as a table. And it is possible to have the so-called time history plots. So just put a measurement points into a model and track the result values over time. This data also can be exported at the end as a table to be used in third-party products. One interesting application is the evaluation of forces and movements of tools. So in one of the previous webinars, we have already seen this example. So basically, it is possible to track how much force is acting on a certain tool. And if we see that a certain tool isn't experiencing any forces because whatever reasons, then it might be desirable to replace this tool or to remove this tool completely from the model and from the assembly. So basically this makes the fixture cheaper without many changes in the results. The results, of course, can also be represented as a best plot, so as a curve between lines. So it is possible, of course, also to see this typical residual stress pattern we usually see in welding simulations and welding measurements. So the question remains, what will happen in the future? And here I would like to start basically with a small look back. 15 years ago, this number is well, has two meanings. It's 15 years from now as we started with the development of Simufact Welding, and as a coincidence, 15 years ago I have started with welding simulation. So 15 years ago, welding simulation was basically very academic, and it was more or less about how to weld two plates together. And how to predict distortions and maybe residual stresses here. For the assemblies were relatively small and relatively simple. Nowadays, we deal basically with something like half of a car body with a lot of sub-assemblies. So here at the bottom part, we have some substructure, then some parts are added to it, then some other parts are added to it, some other parts are added to it. So we have a very, very big models at the end with a lot of additions that are basically not what classical welding simulations thought to be. And the main, one of the main challenges is the interoperability. So it is not sufficient anymore to say, okay, I have two plates, I can weld them together and I can simulate it, but at the end I need to simulate a complete process chain. And what is possible and desirable is, of course, imagine I start with some type of sheet metal forming simulation, so my components have deformations, residual stresses, maybe hardening, microstructure changes due to forming process. With those plates and sheets, I go into a, in this case, laser welding process. From there, I go to heat treatment. Then after heat treatment, I maybe add some components and make resistance spot welding, heat treatment once again. And then maybe I would like to print something on them, so I do a deposition welding process, maybe local reinforcement or something like this. So this might be a typical process chain we are talking about. And inside the Simufact family, the data transfer, fetching and forwarding of results are basically possible with a single mouse click. Maybe just a bit of explanation. Simufact Welding is one of our Simufact products, but we also have a Simufact Forming product, which could be used, for instance, here for sheet metal forming. And we have an additive product used for powder bed fusion processes like selective laser melting and selective laser sintering. So all these products can be coupled together. Of course, one would also like to use some third-party products, and for the third-party tools, we have a universal file interface. It is an open readable file format which includes results in deformed meshes. So with this format, it is possible to transfer the results from and to third-party software. And for more complicated tasks, we also have an interface to the so-called Mpcci Mapper. This is also a third-party product which allows data transfer between basically more or less whole computer-aided engineering environments that are present on the market. The next point would be the model automatization. The GUI as we have it is relatively easy to use. It's actually very, very simple. But often you have to do the same task over and over again. For instance, if you would like to take a look at the influence of welding sequences, of lamping, something like this, you would need to set up or to change models manually over and over again, which is not very convenient. So this is why we have introduced a Python-based scripting capability, which allows you to set up and to change models based on scripts. So basically, if you would like to change the welding sequence in a complicated model with, I don't know, 30, 40, 50 possible sequences, you can just put them into the script, let the script run, and the script would create, out of one initial model, it would create 40, 50, however you want, modules with changed welding sequences. Then they will be calculated and you can compare them with each other. The next pain point or the next challenge is the mesh generation. It is often an obstacle and leads to a significant slowdown of model setup. So you need a nice finite element mesh to be able to do good simulations. So we have our own measures. We have the welding Apex bundle. So Apex is a MSC tool with CAD capabilities, meshing, and also Python-based scripting interface allows to do a lot of things automatically. And the idea is to couple those tools together, not only as a bundle, but really as one tool, more or less. Allowing to pass data between Simufact Welding and MSC Apex, and allowing MSC Apex to create and maybe automatically mesh geometries needed for the welding simulations. What you see here on the right side is basically a model we used for deposition welding, where it was actually possible as a prototype to create geometries and meshes directly out of the G-code. But this is something which is at the moment in the development status, and we will see how far and how fast we will come further with this topic. Next issue would be the artificial intelligence. So in general, the welding simulation is very, very non-linear problem, and this means that small variations can lead to high variation of results. So you see here, the change in the problem itself is very, very small. It can lead to a very fast changing solution. So on the one hand, if you would like to investigate some type of a process window, so a real parametric study, you need a lot of calculation time. On the other hand, estimations are difficult because they can be very wrong. So if I land not here but here, I get a completely different solution. So the idea is maybe the artificial intelligence can help us to evaluate model input and to understand what will happen with results if the model input changes. The next thing might be, I have already spoken about it, is the calibration of heat sources. So at the moment, we have some empirical estimation formulas. They are present in the documentation, and in the upcoming release, they will be implemented in the software. At the end, it comes down to some type of tryout. So I need a cross-section, then I need to take a look at my results, and then I need to estimate how I should change my input to get the proper heat source description. In the future, we are working on some type of automatic calibration tools, but those tools will still need some kind of calculation time. One can also do process simulation with some additional third-party products, or one could think about creating and feeding a database with a lot of welding parameters, so like welding velocity, laser power, and so on, and let the database be clever enough to predict what will happen with the melt pool, or maybe even to suggest what welding parameters are the best one. Same also holds for material data. So small changes in alloy composition or heat treatment lead to huge changes of material data. At the moment, we have the possibility to scale it, to try it out somehow, to try to match the data you have. One can do a lot of measurements. They are usually very expensive. One can calculate, simulate the material data with certain quality of results afterwards. Or also maybe it is possible to feed some type of a database with some intelligence behind it, with alloy composition, with the heat treatment process, and so on. And then get the material data out of it. Also can be used for parametric studies. This is the one I have already shown on the left side. If it comes to reducing the number of fixtures or getting the correct process, it is maybe possible to have an intelligent enough database which can provide insight on what results are to be expected if we change something in the model. We have tried it out here as a proof of concept. The idea here has been we have an assembly with something like 81 clamps at the beginning, and then we try to evaluate forces and deformations working or acting on clamps, and at the same time controlling the deformation of the assembly. So basically, the idea is if the clamp is experiencing very low forces, it can be removed. But if due to this removal, the deformation of the assembly increases, we have to put it back and remove maybe some other clamp. So after a couple of reruns, we went from 81 clamps to only 8 clamps without big influence on the quality of the weldment, basically on the deformation of the assembly at the end. I mean a fixture with 80 clamps and a fixture with 8 clamps, just from the point of view of the price of this fixture, are two very different worlds. So this would be for me for the moment, and I would like to ask you kindly to ask questions if you have any. Feel free to contact us if you have any questions. Okay. The first question is already there. It's about basically the calculation times I have shown on the slide with 86 hours, 2 hours, and 8 minutes calculation time for different types of calculation approach on the same assembly. The question is basically what kind of PC we have used. So the first information would be, so all of these 3 simulations were carried out on the same machine, because otherwise it wouldn't make any sense to compare them. And we usually use a dual Intel 7 Xeon processor with something about 3 GHz and with 8 cores, I guess 8 cores per CPU, so overall 16 cores, and 64 gigabytes of memory.